All right, so we're going to do some more examples with the results that we just came up with. So here, I'm trying to find f prime of x, where f of x is equal to the natural log of secant of x. Once again, we have a composite of two functions where the natural log is on the outside. And what we saw is that when we find derivatives of the natural log of a function of x, the result is the derivative of this function over this function. So what is the derivative of secant of x? Well, it's secant of x tangent of x. And that's being divided by the original function, secant of x. But notice that the secants cancel each other out, and I get this much simpler function, tangent of x. So that's pretty interesting. Now this one will show up again later on, as far in the future as the end of chapter 4 and kind of into chapter 5. And the reason for that is because once we get to that point in this class, we're going to be talking about the concept of anti-derivatives, which are basically, instead of taking a function and finding its derivative, you are given a function and then you're trying to find another function which has the first as a derivative. So for example, we know that the derivative of sine of x is cosine of x. That means the antiderivative of cosine of x, or one such antiderivative, it turns out there's more than one typically, one antiderivative of cosine would be sine. Here, if I asked you to find an antiderivative for tangent of x, that's tricky because if you look at all of your differentiation techniques, none of them that we've talked about produce a tangent of x by itself. But this function turns out to do that. Don't worry about that right now. That's something we're going to talk about later. I just wanted to point that out really quick. Okay, here's another one. We're evaluating the derivative of log of x squared over x cubed plus 1. Remember, if you just see log with no base indicated, it's implied that the base is 10. I could go straight to my differentiation formula right away, but the part of the derivative would require me to use the quotient rule because that's the function that I have on the inside. It looks like a quotient. And even though that's not necessarily a problem, I would actually prefer to do something different here. It's something that we're going to be doing more of in a little bit. The logarithm functions have some very, very useful properties that we want to exploit here. And that's how to expand a logarithm where your argument is made up of products, quotients, powers, or some combination of those. So if you remember from algebra, this is the same thing as this. Okay, I've expanded this logarithm. If I have the logarithm of a quotient, I can take the log of my numerator minus the log of my denominator, and then my numerator is x squared. So this would normally look like log of x squared, but I can also bring powers out to the front of logarithms. And what this does is it makes it so that the argument in each one of these logarithms is much simpler than what I started with. So taking derivatives of those is not very difficult. Let's do this guy. What's the derivative of 2 times log of x? Well, this would be 2 over x times the natural log of the base of this logarithm, which remember is 10, okay? Minus, for this one, I have to take the derivative, let's go like that, of the outside function, which remember is going to be 1 over the argument, which is x cubed plus 1 times the natural log of 10 once again. And normally I'd be writing 1 over that, but because I'm dealing with a chain rule, I'm also going to be multiplying this result by the derivative of the inside function. And that's just going to end up in the numerator anyways. The derivative there would be 3x squared. I'm not going to worry about trying to combine those into a single rational expression. That's going to be my answer. Okay, so notice I didn't need the quotient rule anywhere. I was able to use my logarithm to break this thing down into easier to manage chunks. We're going to revisit that very soon. Okay, here's a very important function. Your book does this as an example as well. And we need to know this derivative when we get to antiderivatives later, like I mentioned previously. So for this, y equals the natural log of the absolute value of x. One thing I want to point out is the natural log function has a graph that looks like this, right? And this is a very rough sketch, obviously. That's 1 right there. The natural log function is not defined for negative numbers. It's also not defined for 0. But if I put an absolute value around the x like this, then even if x is negative, the absolute value will make it positive before passing it along to the natural log. So that means that I can plug a negative number in for x, and then I'm going to end up with a positive, which I can take the natural log of, which tells me that negative numbers are in the domain of this function, even though they're not in the domain of just the normal natural log. Furthermore, this absolute value in here makes this an even function, which means the graph is just going to look like a reflection of the natural log function across the line x equals 0, across my y-axis. Okay, so this function is defined everywhere except for 0, because there's still a vertical asymptote there. But what does the definition of this function look like? Well, this is equal to, remember when we defined the absolute value function back in chapter 2, we said we could look at it as a piecewise function. It's equal to the natural log of x when x is positive, because the absolute value wouldn't do anything there. And it's equal to the natural log of negative x when x is negative. Now remember, it's better to say the opposite of x instead of negative, because if x is already negative, putting this minus here makes this positive, which is what makes the natural log doable at that point. But this is how we define this thing. Okay, now y prime is equal to the derivative of this, and for a piecewise function, if these two functions are differentiable on these domains, which they are, I can take the derivative of each one independently. So let's look at that for a moment. What is the derivative of the natural log of x? Well, the derivative here, excuse me, is going to be 1 over x, right? When x is positive. And what is the natural log of negative x? Well, what's the derivative of the natural log of negative x, I should say? Well, in this case, we can use the chain rule once again, and the derivative of this is going to be actually, instead of the chain rule, let's use what we did before. So that it's going to be this argument in the denominator, negative x, and then the derivative of that argument in the numerator, which is negative 1. That's when x is negative. Okay, but notice that these negatives can cancel each other out and they both become positive. So now what we have is a piecewise function that's defined exactly the same way for positive values of x as it is for negative values of x. And what that indicates is that I don't need to think of this as a piecewise function anymore. I can literally just say that y prime is equal to 1 over x. Okay, now you might be looking at that and thinking, like, that's the same thing that we got as the derivative of the natural log function. So it shouldn't be that surprising that, we're getting the same result here. But I do want to point out that notice the answer doesn't have an absolute value in it. It's literally the exact same derivative as what we had here. But the benefit of this function is it's got a larger domain than the natural log function by itself. So again, once we get to antiderivatives, when we're trying to do this process in reverse, if I say, what is the antiderivative of 1 over x? We're looking for a function that has this as a derivative. And so far, we have found two functions that do that, the natural log of x and the natural log of the absolute value of x. Notice, though, that the natural log of the absolute value of x includes the natural log function right here, right? It's just that it has more to it. So when we get to antiderivatives, we're going to be calling this thing this is going to be our preferred antiderivative of this function because it gives us a larger domain to work with. Okay, we'll revisit that again once we get to that point in the course where we're talking about antiderivatives. Okay, so one of the examples on the previous page showed how we can use logarithm properties to make derivatives involving logarithms easier to do, easier to manage. Now, this particular function, I'm going to be finding the derivative of this, and by itself it looks horrible. It's got places where I would be using the chain rule because I have, expressions that are being raised to powers or radicals of some kind. It needs the product rule because I have a product of functions here. It also needs the quotient rule. This would be a pretty nasty function to take a derivative of directly. So in cases like this, where we have lots of products, quotients, radicals, powers, things like that, we're going to use something called logarithmic differentiation. So first, let me rewrite this thing just by making one small alteration. 2x minus 1 to the fourth. I'm going to write that cube root there as x squared plus 5 to the 1/3 power. That's the only change I'm making right now. Now notice the way that I wrote this. Y equals this. It's written as an equation, and I can manipulate both sides of the equation if I want to. What I'm going to do is take natural logs of both sides of this equation so that I have the natural log of y is equal to the natural log of this whole mess right here. 2x minus 1 to the fourth, x squared plus 5 to the 1/3 over x to the 5/6 power. And now, as I did before, I'm going to use my properties of logarithms to break this down into much easier to manage chunks. Because this is intermediate algebra stuff that I'm doing, getting from here to here, I'm going to do all of the steps all in one, and I want you to see if you can verify what I did. So this would be equal to 4 times the natural log of 2x minus 1 plus 1/3 times the natural log of x squared plus 5 minus 5/6 times the natural log of x. Okay? Hopefully you can see how I decomposed this thing using my logarithm properties. Now, if I want to differentiate this, I need to take a derivative with respect to x of both sides. So I'm actually going to just include that in all of these steps. On my left-hand side, what is the derivative of the natural log of y? Well, again, remember, we're thinking of y as a function of x, so this is technically the chain rule, and based on our previous result, we know that this is equal to y prime over y. Okay? So my left-hand side does not give me just y prime, it gives me y prime over y. My right-hand side, even though it looks like kind of a big mess, each individual derivative is pretty easy to take. This is going to equal 4 times the derivative of the inside, which is just 2 actually, I don't need to put parentheses around that, over the inside, 2x minus 1. This next one is going to be 1/3 times the derivative of the inside, 2x, over the inside, x squared plus 5. This guy, minus 5/6, times ln of x, its derivative we know is just 1 over x. Okay? Finally, I don't want y prime over y, I want y prime. Okay? So what I would be doing is multiplying both sides of this thing by y to cancel this y out right here. But I don't want this to stay looking like a y. I don't want to have a mix of x's and y's in this expression. Fortunately, at the very beginning of the problem, we had a definition for y in terms of x. So I can substitute this entire expression in for that y right there. That means I have y prime equals, let me simplify some things up here. So 4 times 2 would be 8 over 2x minus 1. Plus, I'm going to multiply the 3 in there, so I get 2x over 3 times x squared plus 5 minus 5 over 6x, multiplying the 5/6 there, times y, which is equal to this up here, 2x minus 1 to the fourth, cube root of x squared plus 5 over x to the 5/6. Okay, so this is my derivative. Now notice the derivative is very complicated looking, but getting it was not hard because my logarithm properties helped decompose this thing into a much more manageable set of chunks, right? So to recap, what we just did is something called logarithmic differentiation. And these are the steps in logarithmic differentiation. If you have a function of the form y equals f of x, you can take the natural log of both sides of this thing and then use your logarithm laws to decompose the right-hand side or to expand it into easier to manage pieces. Then you differentiate implicitly with respect to x. So the implicit differentiation takes place on the left-hand side, where we have the natural log of y. That becomes y prime over y. The right-hand side should all be in terms of x. So once you have decomposed that, I should actually do this. I should put square brackets around that. Once you've decomposed that into these little pieces, it's easier to differentiate. Then finally, because my left-hand side is not y prime, but y prime over y, we multiply both sides by y and replace that y with the original function. Okay, that's called logarithmic differentiation. Now, I've taught this class several times, and one thing I've noticed is that when I teach logarithmic differentiation, once students are able to see how much easier it makes certain types of derivatives, they tend to try and overuse this technique, which means they start to try and use logarithmic differentiation with like every derivative they need to evaluate. And that's not, you don't want to do that. In fact, most of the time you're not going to be using logarithmic differentiation. The time that you do want to use it is when your derivative, or when the function you're trying to differentiate involves a lot of products, quotients, or powers of things, which is what we saw here. In other cases, though, it's not going to be as helpful. So don't overuse logarithmic differentiation. Now, since we've talked about logarithmic differentiation and we've seen how it's useful in derivatives of these types of functions, there actually are a few other cases where it's really useful. One thing we can do with logarithmic differentiation is we can derive the general version of the power rule. So back in 3.1, we gave the product, the power rule, and if you remember, we proved it, but only in the case where we assumed that the function was y equals x to the n, and n was a positive integer, because we needed the binomial theorem in that proof. But then after that proof, we said even though we only were able to prove this thing for positive integer powers of x, it actually works for all real numbers that could be put in this exponent here, all real numbers n. And we mentioned back then that we can't prove it yet, but we'll be able to. Now we are able to. So in order to prove the general power rule, let's let y equals x to the n, and we're assuming n can be any real number now. What we're going to do is do logarithmic differentiation. Now, this is straight out of your book. You'll notice they took absolute values first. The absolute value of y, absolute value of x to the n, which would be the same thing as absolute value of x raised to the power of n. They used the logarithm property that allows you to bring this n out front, and this is what's going to make this trick work. Okay, so now when we differentiate both sides, we've already shown that the derivative of the natural log of an absolute value of a function is just 1 over x. If this is an x, or if this is a y, y prime over y, because we're doing implicit differentiation here. The derivative, again, of the natural log of the absolute value of x would be 1 over x times that n makes it n over x. Now, if I solve for y prime by multiplying both sides by y, I get this. Y prime equals n times y over x. But remember, y is the same thing as x to the nth power. So x to the n over x simplifies to x to the n minus 1, and that's the power rule. So again, we haven't established any new information. We already have been using this version of the power rule, but we have been taking it for granted because we never actually proved that it works for all values of n, and now we just have. Okay. There's other times when logarithmic differentiation is useful as well. And that's for that's when we're trying to differentiate functions that look something like this. Now, at the outset, this may not look super complicated, and it's tempting to look at this and think, oh, I can just use my power rule, or oh, I can just use the derivative of an exponential function. But if you're careful and you look at this thing, you'll realize that the function x to the power of x is neither a power function, nor is it an exponential function. And the reason for that is both of those types of functions require a constant to be in one or the other position. So if this were a power function, then I would have x to a constant power. And if this were an exponential function, I would have a constant to the power of x. But in this case, I have variables both in the base and the exponent. So this is neither a power function, nor is it an exponential function. So neither of those rules apply here. But you can evaluate the derivative of this thing using logarithmic differentiation. I can take natural logs of both sides. Natural log of y equals the natural log of x to the power of x, and use my exponent property to bring this exponent out. X times the natural log of x. Okay? Now we differentiate both sides. As we've seen, this left-hand side becomes y prime over y. My right-hand side requires the product rule. So I'm going to have my first function, x, times the derivative of my second function, which would be 1 over x, plus the derivative of my first function, which is 1 times the second function, natural log of x. I don't need to write the 1, I could just say that. Finally, I have a couple of things I need to do here. X times 1 over x is just 1, so this becomes 1 plus the natural log of x. That simplifies. Finally, I need to multiply both sides by y to cancel that y out, which tells me this. Y prime is equal to 1 plus the natural log of x times y, which is the same thing as x to the power of x. This is the derivative of x to the power of x. Notice that the power rule would not have given me this. The exponential function, or the derivative of an exponential function, would not have led me to this either. So we need logarithmic for this to work. There are other examples, I think you have 1 or 2 in the homework, where you're dealing with functions that are similar looking to this. I think one of them is like x to the power of root x or something like that. You still need to apply this technique to solve those. Okay? We're now going to move in the direction of finding derivatives of inverse trig functions. And I think we're going to do this starting with part 3.